Okay, today in this section we'll do 6.3 in your book. That's on the exponential function. And here's a definition. E is equal to the inverse of ln of 1. And also, E is a little bit strange. You can get it in many different ways. For example, E is the limit as n goes to infinity of 1 plus 1 plus 1/2 plus 1/6 plus so on, plus 1 over n factorial. Alright, now E, of course, Euler's number, is positive, so that means e to the x is positive as well, and no matter what x is. And that means, since e to the x is positive, e to the x has a logarithm, because logarithms, as you remember, are defined only for positive numbers. ln of 0 is undefined, ln of a negative number is undefined. So when we take the logarithm, which we can do, we get ln of e to the x is equal to, using the power rule now, bring x in front. That's x ln of e. Alright, and we already know what ln of e is. Log base e of e is 1, so this is x times 1, and that equals x. So ln of e to the x is equal to x. However, the ln of the inverse of ln x is equal to x. Okay? That's because ln and the inverse of ln, of course, are inverses of each other. So the ln of e to the x is equal to the ln of the inverse of ln of x, and that equals x. Now, in a one-to-one function, f of x1 equal to f of x2 implies that x1 equals x2. Ln is a one-to-one function, and so we've got ln of e to the x equals ln of the inverse of ln x, and so that means that e to the x is equal to the inverse of ln of x. This holds for every real number. Now, since ln of x and e to the x are inverses of one another, we have e to the ln x power is equal to x. That's for all x greater than 0. And the ln of e to the x is equal to x. That's for all x. Okay? Now, in your book you should look at examples 1 through 3 on pages 468 and 469, and these are basic pre-calculus examples, so these are things you should be familiar with already. If they look strange to you, then maybe you've forgotten some stuff, or you've never had it, in which case you need to know this. Alright, you need to study pre-calculus. Take a pre-calculus textbook or find out about it online, and be sure you're up on these. You should be able to solve these examples already. These are not calculus. Alright, now let's do a little calculus here. The exponential function is differentiable. Alright, so we want to take the derivative of e to the x. That's basically what we'd like to do. Is it differentiable? Well, yes, because it's the inverse of a differentiable function whose derivative is never 0. And I'm using theorem 1 on page 453 for that. So let's let y equal e to the x. Alright, then you take ln of y on both sides. So ln of y equals x. And let's take the derivative of both sides. d dx of ln y is equal to d dx of x. And we've seen from the last section, d dx of ln y is 1 over y dy dx. And of course this derivative on the right here is 1. And I want to solve this for dy dx, right? Y is e to the x. So what's dy dx? Well, just solve this equation for dy dx. So dy dx, multiplying both sides by y, is y times 1, which equals y. Or, what is y? It's e to the x power. Huh? So what we have is the derivative of e to the x is e to the x. That's so nice. I wish they were all that easy. Well, that's the easiest derivative you're ever going to have to remember. Alright, so I want you to memorize that carefully. The derivative of e to the x is e to the x. Okay, here's another example. Let's take d dx of 5e to the x. Well, you can bring the constant 5 in front of that, so that's 5 dx of e to the x. And so, again, d dx of e to the x is e to the x, so it's 5e to the x. Alright, so looks like it's its own derivative. Now, you may have something other than x, a function of x up here in the power. Of course, x is a function of x, but you may have something more complicated, so we need a formula for that. Let's call it u. So you take e to the u, for example, and I want the derivative with respect to x of e to the u. So d dx of e to some function of x, which is u. Using the chain rule, that's e to the u du dx. And that's about all there is to it. You could write that as, instead of du dx, u prime, e to the u. So let's do some specific examples here. Let's take the derivative of e to the minus x. So u is negative x. Alright, so we've got e to the u du, right? Or du dx rather, e to the u du dx. So that's e to the minus x, and then the derivative of negative x. And so that derivative there is negative 1. So it's negative e to the minus x. Or you could write that as negative 1 over e to the x if you wish. Alright. Let's try another one. Let's take the derivative of e to the sine x. So we can use the shortcut here, u prime e to the u, or the derivative of sine is cosine, so that would be cosine x e to the sine x. Now, this is correct the way I'm writing it here. However, it's prone to confusion because you might think the e to the sine x is inside the cosine, which it's not. So I put a little dot there, meaning multiply. But it's better if you put the e to the sine x in front. So there's no possibility of confusion here. So it's preferable to write that as e to the sine x times cosine x, like I have that written there. Alright, so